Hello, and welcome back to the CST Beginners series, How to Build A. We will now start with episode 3, the Waveguide to Coax Adapter. If we open CST and we will construct a new template, microwaves and RF optical and antennas. Now the plan is to connect this to the previous parts we've constructed. So this will be going on the back of the horn antenna. Because of such, we'll stick with the waveguide and the time domain. As the horn was built in inches, we'll keep this in inches as well. And we're going to stay in the X band, so gigahertz, and then nanoseconds and Kelvin are fine. Frequency minimum, so for X band we'll go between 8 and 12, and we'll look at the E field and the H field. We can call this waveguide to coax and then hit finish. For building anything waveguide, we can refer to the international standards. The standard in question is the IEC 60153-2. This is for hollow metallic waveguides. If you go onto the IEC website, you are more than welcome to purchase this standard for 70 Swiss francs, which may translate into whatever your current exchange rate is for your current local currency. The short version of this is for WR90, we will have 0.9 of an inches for width, 0.4 of an inches for height internally. So if we name our block here, block, and we have our block width as a parameter, as well as our block height. And then we are careful to halve these and make sure the minimums are minused. Oh, excuse me, like so. And then as we're going to keep this as our back, we'll use Zmax as block length. Have our block length as an inch. We'll also have our block height as half an inch and our block width as an inch. So we end up with the following. Now for this to conform with WR90 standard, we need the internal dimensions to be 0.9 and 0.4 as previously mentioned. So if we select the block and also select the face, we can go to Shape Tools, Shell Solid or Thicken Sheet, but inside we'll call this Block Shell, because that's good practice, parameterize everything. We'll make this 0.05. So this will give us a 0.05 shell around the outside. If we select OK, now we can go in and see that it's removed the front face but kept the back face by picking that face. And then if we check the dimensions, you can see here we have 0.9. It's 0.4 as required. This is now to IEC standard for WR90 waveguide tube. 0 to reset the orientation, space to zoom out. Now the next thing to do is to place the coaxial interface onto this. For this demonstration, we'll keep it simple and have a 3-part coaxial interface of a center pin, a inner dielectric, and an outer conductor. We use the midpoints, pick this internal back wall. We can set this as our local working coordinate system. With this selected as our local working coordinate system, we can then transform this to determine where we want to place our coaxial interface. This, in theory, should be offset from the back wall by a quarter wavelength or slightly less. The back wall here is referred to as the back short. So we'll define this as back short. Now, to determine what the back short should be, we've just punched 0.25 in here, just as a random number. We need to understand what our center frequency is and how that translates to our waveguide wavelength. This is slightly different to the free space wavelength. WR90 has a bandwidth between 8.2 GHz and 12.4, with a center frequency of 10.3 GHz. Now we can define that as a parameter as well. So we call that center frequency, 10.3. And then we can work out the wavelength for that within CST by using the built-in function for light. So we call this wavelength in meters, as we're working in meters per second and gigahertz. So if we use C light, which is a built-in parameter, and then we divide that by our center frequency, convert that from into hertz, so by 10 to the power of 9, that gives us 2.9 by 10 to the minus 2 meters per second. Then we can convert that into inches, as that's the units we're working in. We can do this by timesing it by 39.37, which gives us a wavelength of 1.145 inches. We can then work out what the lower cutoff frequency of this waveguide channel is by using the broad wall width, which is the 0.9 inches between these, and the speed of light. So if we call this broad wall, that will be the block width minus 2 times the shell, the block shell, and this should give us 0.9 inches, as we have 0.05 of an inch on either side. And then at the cutoff frequency for the lower is the speed of light, so we can use C light divided by 2 times this broad wall, and then we need to convert this from inches into meters, so we times it by 39.37. This should give us an answer of 6.5 gigahertz. Apologies, divide by 39.37. This is why it's always pays care to pay close attention to your units. As you can see, this is roughly 6.5 gigahertz. We can convert this to have it read as gigahertz by using cutoff lower gigahertz, and then we use cutoff lower, divide this by 10 to the power of 9. That should give us 6.5 gigahertz. There we are. Now we have our lower cutoff frequency, we can find the wavelength for this. So cutoff lower wavelength. We'll use C light divided by cutoff lower. And we can use this cutoff lower wavelength as well as the wavelength in inches, or in meters rather, excuse me. We can use these to work out what the waveguide wavelength is, and we can then compare this with the free space wavelength. To work out the waveguide wavelength, we can break it down into parts. So we can start by, we'll use K as our parameter, and we will take the wavelength in meters for free space divided by the cutoff lower wavelength and square this. We can then take a new variable or parameter, we'll go with P, and we're going to square root 1 minus K, and then we can take our free space divided by this, and this should give us our waveguide wavelength in meters. So we'll take our wavelength in meters divided by P. We should get roughly 3.7. There we are, 3.77. And we can convert this to inches. Take waveguide wavelength meters divided by 39.37 times by 39.37. So whereas in free space our wavelength in inches was 1.14, our waveguide wavelength is closer to 1.5. Now we've defined the waveguide wavelength in inches and all our other main variables, we can begin to start placing parts inside our waveguide tube. Let's work out what our half wavelength and our quarter wavelength parameters are, as these will come in handy through our modelling process. Take waveguide wavelength in inches divided by 2, that's our half. And for our quarter, there's our quarter, 0.37 inches. Now, if we go back to our back short, we can set this to our quarter waveguide wavelength in inches. And if we watch here, now I've done this and hit F7, it will jump to the relevant place. To make sure we can move this about a bit through optimizing and modifying later, we'll minus this by a back short offset. Now this is going to flash red until we define what that parameter is. So back short offset in here, and we'll keep it at 0 for now. Now this is no longer red as it is fully defined, and there's no change as it is currently set to 0. We can now define our coax center pin by creating a cylinder at our local working coordinate system. We can call this coaxial pin, and we want this to be a cylinder in the V orientation, where we'll give this a radius of pin diameter divided by 2, and a V max, where we will, as we're starting inside, we'll punch through the shell thickness, so block shell, plus height of the interface. So we'll call this interface height. Again, for now, let's just pick some general values. So for our pin diameter, we go for 0.05 and our interface height is 0.1. As you can see, this is going to punch through as our pin. Then, to put a dielectric around this, we can select the face of the coax pin, which is the entire wraparound. We can go to modelling and extrude face on this. We can call this coaxial dielectric. We'll give this height of the dielectric diameter divided by 2. and then minus the pin diameter divided by 2. Be careful to check those brackets. As this will be the diameter minus the already internal diameter we have. We set this to PTFE. And for now we can put this to 0.16. You can see this is beginning to form. We'll insert this into, you see the Coax electric into the block. So we're inserting this inside our waveguide section, and you can see it's punched through the bottom. Now, an easy way to view this is if we can put the cutting plane, we'll set this to our current working coordinate system U, and we have a cross-sectional view to see what is going on. We can tidy this up shortly after. For now, let's pick our outside of our coaxial dielectric, and we'll go for our coax outer. This is going to be made from PEC, perfect electrical conductor, and similar to how we defined the diameter for dielectric, we'll do the same here. So outer diameter, and we'll minus the dielectric diameter, both divided by 2, as it's asking for the radius, in this case the height. Go for 0.19 for now, and OK. And we can now see what looks like a coaxial arrangement inserted through our waveguide section. Now for a bit of Boolean algebra, we select our block and hit the / key, which is also referred to as insert, and then select all of our components, hit enter. It tidies everything up, so this section is completely inserted within the waveguide block. So this is our cross-sectional view, and if we turn the cutting plane off, you can see we now have a fairly rudimentary shape similar to what we're looking for. We can now go inside, or if we put the cutting plane on, it may be easier. Now if we select the center circle, which should be already where we are, but just to be sure, and we set our working coordinate system here, we can extrude this face by selecting face and then extrude pin. We'll call this pin 2 for now, as we're going to Boolean this with our current coaxial pin, and height will give of us pin depth. Now from fundamental theory, we know that this needs to be roughly halfway into the waveguide, but backed off slightly for nulls. So for now, as we know the height is 0.4 inside, we'll go for 0.2. We can see this is going to create a pin inside that is halfway cut into the material. Now this will give us not very good performance, but we can see what we have so far in terms of S1E3 measurements. So if we place a waveguide port on the outer to fill this coax, and then a waveguide port on our end section for it to propagate to somewhere, we can run a simulation and see what we have so far. We go to Setup Solver, we'll go to Calculate Port Modes Only. The first thing we can do is check our coax port mode to see if we are getting 50 ohms feeding into the structure. So we hit Start and leave this to run. So just to jump forward, now our results are finished computing, we can check our port modes. So for port 1, which is our coax, is the one we're interested in, check the E field, and we can see that our line impedance is 48.4 ohms, which is incredibly close to our 50 ohm desired, and actually probably within tolerance for a lot of X-band designed coaxial inputs. So for this testing purpose, I'm happy to leave this as is for now. You're more than welcome to go and modify some of the dimensions to bring this closer to 50. What I would recommend looking at is increasing this dielectric diameter to probably 0.165. That is beyond the scope of this video. Now let's run a full solver. So let's disable the calculate port modes only, and we'll calculate a full time domain and just see what sort of performance we're getting now. Now don't be too disheartened if this doesn't look very good. We're not expecting it to be good at the moment because all we've done is put a coax pin inside a piece of waveguide. There are a few more things that need adding, such as tuning pins and some feed probes, but onto that shortly after. Now the simulation is finished, if we go to check our S1E3, we'll see that we do not have a very good match going on. And there's quite a lot of reflections coming back up the coax. We haven't got the isolation we wanted. So, as we've already set this up with quite a few different parameters, we can look to do some clever little bits of simulation with parameter sweeps to see what we can do to improve this. First thing we can do is look at where the interface is placed. We can slide this forward and back and monitor the result to see which gives us the best match. Initially we're set at a quarter waveguide, but if we use our backshot offset we can translate this. So if we go to a parameter sweep, we'll define a new sequence, backshot offset, luckily already set for us. We'll do a linear sweep. Now the theory is it should be a quarter waveguide wavelength or less, so we only want to use a positive number here as we are subtracting. So if we go between 0 and say 0.3, just move this out of the way, that's going to take us quite close to the wall, to the point where the coax and outer may even be penetrating. But this will allow us to see everything that's going on. Now for number of samples, let's keep it fairly rudimentary but in depth enough to see what's going on, and we'll do 20. The video will jump to the end of this sequence so we can see the results afterwards. So if I click start now, I'll see you on the other side. Now that our simulation is finished, we can go and check our S parameters and see what we have come up with. And as you can see, we have quite a pretty rainbow of colours, all showing varied results. Now from this initially, it's quite hard to determine what we're looking for, but if we go through and look at each run individually, we can see as the backshot offset increases, we lose performance at the lower frequencies and gain it at the higher frequencies, up until a point when it all starts to flatten out to very negligible, if not awful, results. Initially, what we're looking for here is a steady, flat response across as much of the bandwidth as possible. So our initial at quarter wavelength is arguably one of our best already, and then it's quite faint to see, but as soon as we start to increase the offset, we do get improved from roughly 9 GHz onwards, but between 8 GHz, that minus 6 dB starts to creep closer and closer to -4. So really, we can take a good estimate average and say only a small offset is what we're looking for. And as we're focused really between 8.2 and 12.4, let's look to about run 3, which has given us quite a good isolation in this region here. So if we right click on 3, we can select parameters, set parameters to run ID, and this will store that parameter from the model. If we do a cut, we can see this is now what we will be using for now as our stored parameter. Next, we can go and do a parameter sweep. So if we clear this one because we're happy with it, we can do a parameter sweep on our pin depth. And simply, the easiest way to do this is to observe the change in pin depth go between 0 and 0.2, as going beyond halfway will actually almost definitely give negative performance. And again, we'll look at 20 samples. And when this is finished, we'll come back and observe what changes we have in performance. Now the simulation is finished, we can go and analyse the results. The first thing I would recommend doing at this point is saving the file. Just in case anything unexpected was to happen, we don't want to lose the work we've already done and have to rebuild the model from scratch. So once the model is saved, we can go and check our S parameters. And again, we have a lovely rainbow, and it's not immediately obvious what we should be looking for. But a feature we can do here, we can right click and use 0D from 1D. And if we click enable here and set it to, well, our center frequency, in which case 10.3 gigahertz, and hit apply, we can see as the pin depth increases what our magnitude at 10.3 gigahertz is. And it's clear there's a very direct relationship between pin depth and our S1 parameter. As such, we'll leave this pin depth at 0.2, as that appears to be the best result so far. So we'll go back and use set parameters to run ID. In this case, it's throwing an error, as if we go into our parameter list, we can see that pin diameter, or pin depth rather, is already 0.2. So this is our best result so far. In order to improve the response, because despite it being the best result, it's still not ideal. As we look at just the S parameter here, we turn off 0D from 1D, look at just the result in question, run 20. We can see it's still not very good for a waveguide to coax transition. We really want this to be -20/-25 dB across the entire bandwidth. So what we need to do now is consider how this pin is coupling to the waveguide to coax, as this is 50 ohms coming in and this area around it is not going to be 50 ohms. If we go to 1D results and then reference impedance and check ZRF1, we see we've got that 48.5 ohms coming in at port 1, and at the second reference plane, the second port, we've got between roughly 660 all the way down to about 450 ohms. So we're looking at about 500 around our 10.3 gigahertz range. So in order to couple this correctly, we need to consider placing a feed probe somewhere on here that is either larger or smaller, and also, so we need to think about the diameter of this probe. Is it going to cut in or is it going to extrude out? Is it going to be longer or shorter? And how is it going to intersect this current piece? In order to do that, given that we're already at this point here, we can model a second cylinder. We can call this feed probe. Outer radius, we'll call it probe diameter. Now we don't know what this is at the moment, so we'll just give it a random variable, we'll say 0.15. for Vmax, we can put anywhere between, let's say, infinitesimally small, maybe 0.01, all the way up to 0.2, because it might cover the whole thing. So in which case we can use probe, what should we go with? Probe height. And we can declare that as 0.01. Make sure to put the minus sign as we want it pointing downwards. If we place that in, that then locks that in place there. And this is bound to local working coordinate system. So if we open our history list now and roll back to just before this, run to here, say we want to place that part further down, we can open transform WCS, work out which orientation, so we might want to move it up and down, so it's our DV, and we've already used probe height and probe diameter, so let's go with probe position. Remember to use the minus sign as we want it going downwards. And just to be sure that it is going in the right position, we'll start it at 0.2, and this should jump our working coordinate system all the way down to the bottom of the feed pin, which it is. And then if we step, we'll notice it's now placed in, and it's placed in below because of our choice of using minus sign. Now we don't know what we want these parameters to be, so we're looking at the probe height, the probe position, and the probe depth, or probe diameter rather. Probe height, for example, could be 0.1, in which case it would be quite large, and it would be a big stub sticking at the bottom. Probe position, we might only want it to start halfway down, so we could put that as 0.1 as well, and it will cut through from the middle onwards. And our diameter could be absolutely massive at about 0.3, which I highly doubt, but the thing is, this is something we're not sure of yet. So now what we can do with our parameter sweeps, so we can do a new sweep with new parameters, where we will take the probe diameter. Now it's probably not going to be 0 because we're placing it in. So let's start with what we've got so far as 0.05, 0.06 to have it slightly wider, and then we'll go all the way up to 0.2 to be quite chunky. We'll only do 5 samples, and you'll see why shortly after. And then we'll also add the probe height, so where it's starting. Sorry, no, rather, the probe height is the total height of it. So this needs to have at least some height, so we'll start at 0.01. We're not sure yet, it might want to be the entire height of the probe, so we'll go to 0.2. We'll make this 5 samples. And then probe position, we could start it at the very top, we could start at the very bottom. And then we'll use 5 again. Now this is going to definitely produce some very erroneous results that won't be suitable for what we're doing, but in order to just brute force this to observe what is happening by modifying these parameters, we'll just leave it as this. Now the reason we've gone for 5 for each is it's going to compute each variation between all 3. So this, if you do a quick calculator sum, will be 5 times 5 times 5, which is 125 results. Now this is why I recommended saving first, as this is going to take a little bit of time on your system if you are building along. So I'll close for now, hit save, and go into our parameter sweep again and get ready to hit start. Then I can leave this to run and perform other tasks. Maybe if I've got the tokens, do some other modeling on a different project and just leave this to run in the background. So I'll start this now, and when it's finished we can look at 125 different results and see what sort of key factors we're looking for to improve the performance of our waveguide to coax adapter. Now this is running, this concludes part 1 of the waveguide to Coax adapter. In part 2, we'll establish what we've learned from the results so far, and we'll work out the ideal probe position, shape, size and everything else. And we'll go on to discuss placing pins or screws at the bottom of our channel to improve the bandwidth and further increase our performance. They'll go somewhere around here and somewhere around here. I look forward to seeing you all there. Thank you for watching along, and if you have any questions, please contact us directly at sales@castlemicrowave.com or leave a comment in the comments box below. Thank you and have a good rest of your day.